Okay, so now let's just quickly generate the mesh for this problem and solve it quickly. So I have already generated the geometry and the mesh here, and it is really similar to the previous one. Previously we used a monopole with an outer boundary, and now we just have another circle here. So pretty simple. I'm not going to show that. So we'll just be using linear triangles in this case, and we can just keep refining so that the boundary is represented better. And on the outer boundary we have a zero flux condition. On the inner boundaries we have dirichlet conditions. So for 4, the physical flag 4, we have phi is equal to 50. For 5 we have phi is equal to 0, right? And in this case we have no Robin condition, because it would be quite difficult to compute the Robin condition for these two dipoles. But a zero flux condition works really well so long as this radius is kept, the outer radius is kept fairly large. And so we'll use a zero flux condition, and in this case a zero flux also acts as a do nothing condition, because if you remember, this was our weak form, and if du by dx is just 0, then we just don't have to change the matrix structure. So we just keep the stiffness matrix entries, and this guy we put to 0. But since generally we always initialize in any code, we initialize the force vector or stiffness matrix as 0 values. So this is typically called as the do nothing condition. And that is why we have in our mesh reader file, we have these excluded flags. So whenever you just exclude the flag, it will just naturally impose the do nothing condition. So if there was an internal boundary, the do nothing condition would mean a flux balance, because at internal points, so if you consider this point, really you have a flux balance over all of these. So because your stiffness matrix entries are not just coming from one side, but they are all over the domain, right? So I mean from all directions of the domain. So your stiffness matrix, so if I was writing the row for this node in the stiffness matrix, so I would get the contribution from all of these 6 elements. But for the boundary case, I would just, if I was considering this node, then I would just get contributions from three of these elements, so only from one side. So this doesn't represent a perfect flux balance, rather this is more like an insulation. So when you have an excluded, when you exclude the boundary flag, and if it's an internal boundary, this will act more like a flux continuity. So it will just do the same thing as before, that is the stiffness matrix, and naturally you always have force vector equal to 0, because that is how you initialize. And unless you have an internal source, in that case of course the force vector will have some values. So so that's about the boundary condition, and we'll be using simple linear meshes. And let me also show you the regularization for the higher order meshes. So in this case we'll just be using linear elements, but I just want to show you what is the regularization. So here I have made a very bad mesh on this this circle, and I have done this by using transfinite. So I'll just show you the script. So in the script I have just used transfinite. So transfinite means you choose the number of points on an element. So for this you just click on curve and click on the boundary which you want to select, and you just prescribe the number of points and you press OK. And of course Gmesh will just optimize, and it will try to make sure that those number of points are added. So it might go up and down based on what's possible with the mesh quality. So so this is your mesh, which is a very bad quality mesh, and you can see that this is just a triangle for the circle. And now when I put set order as 2, you can see that this has become a hexagon. You can also use set order 3 and so on. So really the point to notice here is that this element has become concave, the angle has become lower, and the Jacobian is also reduced. So we can really optimize this by using higher order optimization tools. And here you have your regularization strategy, and I can just increase the Jacobian range here, and you can see that this should change. Right, so now you can see that it is just trying to increase the Jacobian, and it is trying to make the element less concave, but obviously it is also controlled by this point. So it will just try whatever is possible based on the algorithm, and if it fails, then it will just give you that error message, right? So now it is just trying to skew this, but as you can see, these elements have a higher aspect ratio. So really the correct strategy is to add the required number of points, but it is not always possible depending on the physics or the model which you are using. In this case, it is really simple. We can just use a very we can just use the mesh which by default Gmesh is giving without prescribing any transfinite points. So now you are seeing that okay, optimization failed. It is showing this message in red because it's not able to optimize for this Jacobian. So really this is just to show you the effect of Jacobian on the mesh, and how you can use Gmesh to tune this, and we can also tune the number of layers, the distance, and so on. So this is really important for turbulent flow modeling, where you have to define a wall function, and there the number of layers and all of these other factors will become crucial. But in this case, really we can go with the default mesh, and let's just do that. So we can have a look at these points for mesh generation in more detail in the next course, which will be about Navier-Stokes modeling. So let's just define this mesh, and okay, I just have to reload the script, and yeah, so now I have removed the transfinite. So let me just refine this. So now you can see that the elements are a bit skewed here, so I can again just go in the mesh and just change this. Right, so now you can see that they are more isotropic. We could also run a check on the angles for each triangle and ensure that they are more closer to an equilateral case. And okay, so let me make a slightly coarser mesh because finer mesh is not really required here. You can just reload the script, and alright, so that's okay. Now let's just export this quickly, and let's call it circles P1. So 4 and 5 are our internal boundaries, and 6 is our external boundary. So let's just use our Gmesh reading file, and in the excluded flags we'll just put 6. So this is the code that we had just used for the monopole. Let's just change this. So this is okay, so this is already defined as circles p1.m. So so this is our mesh file, and let's just put the excluded flag. Then let's just add the directlet conditions. So this was the previous directlet condition, phi inner at 50, the same one. We just have to plug in the boundary info. So the boundary info is 4 and 5. So alright, so inlet nodes are 4 and 5, so that is correct. So here we just have to prescribe phi outer, which is 0, and these nodes will just be our outer O nodes, which is not really the outer nodes here, but just the cold cylinder, you could say. Alright, so let's remove the Robin loop. And now we want to add the reaction forces. So let's just define a stiffness matrix without the boundary conditions. So we'll just define this before applying the boundary conditions, and after the post processing starts, we can just use this matrix, multiply it with the solution, and you get your reaction forces. And we'll just extract the I nodes and O nodes, these guys, boundary flag 4 and 5, and those will just be our reactions. So so that's it, and now let's solve this problem. Right. This is our solution, and you can see that okay, so let's also generate the analytical solution. So this is the analytical solution from Greenberg, and here you can see the Q, which is the flux in the hot and cold case, is also defined. So let's just run this and we'll get the comparison. So now first let's look at the solution. So this guy is our analytical solution, and on the left you have your FEM solution. So these are almost the same. The primary difference that you can see is the curvature here, and this curvature will really start matching as you increase the radius. Okay, that is because the outer radius is basically a truncation, and right, so this is our geometry, and as we just increase the outer radius, it will just start simulating more and more closely the effect of the infinite domain. Let's also look at the reaction forces. So the reaction forces for your inlet, which is basically set at 50, so you are getting it as plus 135.7 almost, and this is your analytical case. So in the analytical case, you are seeing a minus sign, and that is correct because the flow is outward. And in this case, this is a reaction force, which is the opposite force, which is basically maintaining the Dirichlet condition. So that is why it has a sign of plus. So since it is the opposite direction force, so you just have to reverse the sign to get the actual flux. Okay. So it is the actual flux from reaction forces is basically minus 135.7. So and the reverse case just exists at the other cold cylinder. Okay. So now let's just edit our script and use a slightly larger outer radius. So let's make this 25, and let's just reload the script, mesh it with 2D. Let's refine. Okay. Let's export it again to the same file. Alright, so now you can see that the reaction forces are more well matched. It's almost 137, and let's look at the analytical solution. So now you can see that this has become slightly more flatter, and I must mention that this is a bit misleading because the outer circle is still fairly small, and so you can see in the analytical solution, you can see this in the analytical solution, and though the reaction forces are matching more closely, this value can be more misleading. So the actual the actual method is to just do a mesh refinement study, and you could also refine this mesh, and we'll just export this, and you will really see that the value of the reaction force will drop, and that is because of the truncation error. So this will be slightly slower because, okay, so now this is your reaction force, and now you can see that it has dropped. It has dropped from 136.99 to 136.75. So yes, of course, as you make the radius larger, it approaches asymptotically the 137 kind of value, which is the analytical value. But as you start refining the meshes, you can see that this is going down. So for R is equal to 25, you can again do a mesh refinement study, and you will see that like it will asymptotically converge to something like 136, just lower values of 136. And in case of outer radius as 12, this will converge to 135. So those are really the correct values for your numerical simulation, and you could make a coarser mesh, a really coarse mesh, okay, and so let's just run a very coarse mesh. And now you can see it is 137.9. So this is really misleading because really you can get misleaded by being close to 137, but really you are using a coarse mesh, and a coarse mesh is not accurate. So really it's important to do the grid convergence study and get an asymptotically convergent value for the case of radius which you are using. And you could also add more number of points here so that the truncation is captured well instead of just putting coarse elements here. So that's the point which I wanted to emphasize, that the grid convergence study is really important, and just because you are getting values close to the analytical solution doesn't mean that those are correct. So you should always do a grid convergence study. So that's about it for this problem, and you can see that we can just calculate the reaction forces very easily doing the integration of the secondary terms, or rather the secondary variables, which in this case is the flux, is very easy. So that's the strength of finite elements also. It can handle the boundaries really well. So if this was a bubble, in Navier-Stokes case, you could model the stress on the bubble, and you could integrate the stress, which is important for your Marangoni stress or for your normal stress. So a liquid-liquid interface is more like a stress jump or a force jump. So you can really so Navier-Stokes is a momentum balance, so you could also think of it as a force balance, and so really you can rather it starts from a force balance, you could say. That's one way of looking at it, looking at the derivation. And so the terms which you get on the interface, in this case the secondary term is the heat flux or the flux, and in the Navier-Stokes case it is the stress. So you can model the stress jump on a liquid-liquid interface very easily, even if if you have put marker points on this mesh, or you are using a moving mesh, then you can just even if the mesh is deforming, exactly you will get the normal and the tangential components. So in that case, those are vector equations for Navier-Stokes. So the stress is basically a tensor which is contracted to a vector, and so it has x and y components. In this case, your flux is a vector which is dotted with the unit normal. In case of Navier-Stokes, the stress tensor is dotted with the unit normal, and that tensor just shrinks to a vector. So we'll see all of that in the next course, which is on Navier-Stokes. So let's not bring that here. And I'll be providing scripts in Julia and in Python, in MATLAB, and in those scripts really I will also be providing the code in sparse assembly, right? So sparse triplet assemblies. So this will allow you to really use small meshes, and when you use sparse triplet assemblies on MATLAB, you can easily go to 1 million kind of DOFs as well. So really it's powerful. So here we have not used any sparse allocation, so we are really storing all of the zeros. But in the code which I provide, you will have that. So you will be able to really refine the mesh as much as you want. So in the case of Python, obviously you are using the .msh file, so you will have to use that export. In case of MATLAB and Julia, you can use those .m exports, and so the kind of exports of the circles.m, so .m export of from Gmesh, you could use that, and the instructions are also given inside the driver. So maybe I'll just run this once in front of you so that this is more clear. So yeah, so this is the Python folder, and here I have just divided it into a bunch of scripts really. So you have a driver script, because this gets a bit long because I have used the triplet assemblies. So you can see that I have rows, columns, values. So this is your triplet assembly. So this gets slightly larger, and the boundary conditions also have to be imposed with slightly more syntax. So I have just separated these instead of putting them in one file, and you can just run this, and you can see that here I have a ptp1.msh. So you can just add this, and in a very similar way, inside the driver you have just a test case, and you can see that in the test case you have ptp1.msh. so you can just add the file which you want. You can add the BC flags, inlet and wall. So wall just means directlet equal to 0. So everything is mentioned here. So you have the comments as well, so you can just use the file based on the comments or just modify it. So this is exactly our solution. So matplotlib gives you really nice nice plots. In case of Julia, I really did not like the plots, and so I have just given paraview export file. So I have given so this is our Julia file, and so it's really the same, exactly the same case. You have a test case here, and you're reading ptp1.1, and you're giving inlet, wall, inlet profile. Really the same thing here. You are using an M file of which is exported from Gmesh. You have a Poisson solver. Again, in the Poisson solver you have triplet assemblies, right? IJV, these are your triplet assemblies. So I'm not really going to explain this code. It's really a change of syntax rather than a change in the finite elements. So this just helps you crank up the total number of solvable DOFs. So I can just run, okay, I just have to run the driver. So once I run the driver, I'll just get a solution, and you have a write VTP file here, which will write a VTP file which can generate this solution.vtp, and this you can just open in paraview. So I have given the links for downloading Julia, Python, paraview, VS Code, all of these, just in case you want to use them. And really I cannot make a course, I cannot introduce tutorials on using paraview or using VS Code. So I'm really assuming that if you're using this language or the software, you are able to use them, because I really have a time constraint here. So I'm sorry, I cannot do that. So I have just plotted the solution here. You can see the total points here. So this is just me exporting the solution.vtp file, and then I'll just add a filter Dipole, which is which you can get as, why am I not getting the filter? Okay, I just have to apply this first. Okay, so go into alphabetic and just put the Dipole 2D, and this will just give you a nice surface plot. And you could even do contours on this. So there's so much that you can do inside paraview. So these are your contours, and you can just So for some reason you cannot really add the values over the contours. This is really a drawback of ParaView. I'm surprised how it's not really possible that easily. Right, so you can even see the contours, and you could keep refining the mesh, and you could have a look at the solution. So you can do post-processing inside this as well. So okay, so that is how you can run the Julia Python scripts which I have given, and I will also be giving a MATLAB script. In the MATLAB script, I will also provide a really comprehensive shape library, and this shape library you can call by using element type and order, and this is already integrated into the actual solver for MATLAB. So this will be the actual solver, and again you have a sparse assembly here with separated Poisson solver with a nice sparse assembly. So again you have these IJV vectors, which is your sparse assembly. So you could have a look at this code, or you can even tell ChatGPT to just change your working code into sparse code. That is very easy, and then you can just run this by specifying the kind of mesh which you want. So I have given various meshes here in case of MATLAB. PT-P1 is your mesh for your P1 triangles, then you have P2 triangles, P3 triangles, and Q1, Q2, Q3 are for your quads. So really there is no change, you just change the shape library and the indexing, and that change has been assimilated into the Poisson solver already in the form of case 1, case 2 and case 3. So you can just switch this, and you can just switch from quads to triangles really easily. You can run this to get again the same kind of reaction force values and your solutions. So the analytical solution is also automatically plotted, and I'll also give this this shape library in each and every Python and Julia script as well. So this will really have us. This will really help us to understand how these elements work, and if you want, you could integrate that shape library into your Python script as well, and you could make a similar change in your Python script. So this is about it, and this is your 2D mesh so for your Laplace problem, and I am also giving a script for quads up to cubics and triangles up to cubics as well. So the Gauss rules are also included, and the analytical solution is also included. So you can have a look at it, you can play around with it, you can add in any mesh file which you want, and you could just manipulate it. So this is about it. This is for the 2D case, and in case of an assignment actually, which I will be putting on Udemy, not on YouTube, because on Udemy we will have a more structured look at the course. So we'll be running the method of manufactured solutions, where we'll just look at the convergence rate, and so that will be the end of the 2D, and in the next session we'll take a quick look at 3D, which I will not live code. I will just show you how the changes are made, because I'll just copy paste the blocks which are pre-coded, because really you just have to change the Jacobian of transformation. You just have to make this bigger, you just have to change the shape library, the Gauss rule, right? And really the internal structure is almost the same. You just have another term here in the Laplace also along the z direction, and that's about it. The reaction forces are also the same, everything else is the same. So there is not really much change from 2D to 3D. So we'll do that really quickly, and that will mark the end of the main part of the course. And then we'll also look at a workflow in Phoenix, where we'll generate a Python script in and run it in Phoenix, for the same problems which we have studied, and we'll also look at the same workflow in a GUI tool, and that will be the end of the course, and that will also be a segue into the next course, which will start off with the same kind of Laplace kind of equation. That course will be for Navier-Stokes. In that, we'll solve the potential flow across the cylinder first, which will just start off with the same Laplacian code, and then we'll do the full Navier-Stokes. So I thank you for your attention, and I'll see you again in the 3D meshing and the 3D solves. Thank you.